Okay, let's start with just few words about introduction. First of all, good afternoon to everybody and welcome to this third talk of the Women in Logic series. So about the series, the talks take place every 2 months, so the next talk will be in March. And they feature prominent figures in the field. So the inaugural talk was delivered by Valeria de Paiva, which is the visionary behind the Women in Logic initiatives. And then the second talk was given by Laura Kovacs, who actually just got her fourth ERC grant. And both, they set a high standard for this inspiring series of talks. So just a quick reminder, Women in Logic is an initiative aiming to provide a forum that brings together women working on various aspects of logics, from foundations to applications. And like as a small add, the talks of the Women in Logic series are organized by the Vienna Center for Logic and Algorithm. You see VCLA in our background, which is an initiative of the Vienna University of Technology to promote international scientific collaboration on logic and on algorithm. I'm Agata Giabatoni, and together with Stefan Seider, we are leading this VCLA. But now I'm done with my introduction, and I'll pass the floor to Josephine Dick, who will introduce today's speaker.
Yes, thank you, Agatha. It is my great pleasure to introduce Francesca Poggiolesi. Francesca is a CNRS Directrice de Recherche full professor co-leading the Logic and Philosophy of Mathematics group of the IHPST in Paris. Broadly speaking, her research interests cover both foundational philosophical issues as well as more technical logical problems. And the common core of these different perspectives is represented by the employment of a similar methodology rooted in proof theoretic tools. In the last year, she has been focusing on the notion of explanation that she has been analyzing in different areas ranging from mathematics to explainable AI. Her research has been awarded by the French National Agency of Research with the 4 years grant Bolzano Insights. She is the author of the book Gentzen Calculi for Modal Propositional Logic and one of the editors-in-chief of the Journal of Philosophical Logic. Welcome, Francesca. Some practical things before we get started is that we do not have the chat enabled, but we have the Q&A. So if you have any questions that pop up during the talk, you can ask them. And after the talk, we will go over them and Francesca will answer them. Thank you so much for being here. And the floor is yours, Francesca.
Okay. So first of all, I would like to thank the organizer for this very kind invitation. I'm a great fan of the Women in Logic seminar, so it's really an honor and a pleasure to present my work in this framework. So I will start my talk by briefly introducing the framework where the talk takes place, and also by clarifying the aim of the talk and the structure of the talk itself. So to do so, I will start from the notion of proof, which together with other few notions like truth or knowledge is one of the milestone concepts of logic and philosophy and science. And when it comes to proof, there are several questions that naturally arise. And among them, there is a question that has particularly attracted my attention, and is the question, what are proofs for? So what is the goal of the proof? Why do we prove stuff? Now, it turns out that since the antiquity, two different answers to this question has been provided. So on the one hand, we can think that the goal of a proof is to show that something is true. Okay, these kind of proof have been called proof that, and basically they are the proof that we see in mathematical text, standard proof that show that a theorem is true. But we can ask more from a proof. We can ask that it shows also why something is true. And we are going to call this second type of proof why. And the idea is that the proof why not only show that the theorem is true, is also show why it is true. It gives the reason why it is true, okay? So I think that the best way to understand the dichotomy between proof that and proof why, and in particular to understand the value of proof why, is to see the distinction within an example. And as an example, I've chosen Pythagoras theorem. So I've chosen this theorem because it's a very simple theorem. We all learn it at school. And so you can focus rather than on the theorem, on the explanatory features of the proof. Okay, so if you look at the Wikipedia page of Pythagoras theorem, you find out that there are at least 9 different proofs which show that the theorem is true. So 9 different proofs that. But amongst these 9 different proofs that, there is one that mathematicians usually agree in considering an explanatory proof. Okay, so a proof that provides a reason why the theorem is true. And I'm going to show you this proof in detail, so that you get the flavor of what is going on. Also, this example of Pythagoras theorem and explanatory proof that comes with it will follow us all through the talk. So please bear in mind all the details that I'm giving now. So the theorems basically say you take a right angle triangle XYZ, and you can show that the square of the hypotenuse is equal to the sum of the square of the side. So how do you prove that in an explanatory way? Basically, you consider a right angle triangle XYZ that it has its right angle in X, and you draw the 8. The 8 is going to be XW. And then you consider first the triangle XYZ and then the triangle XYW, and you easily realize that these two triangles are similar. So why are they similar? Because they both have a right angle in X and in W. They both share the angles Y, so the remaining angle is equal. And if you take 2 triangles and they have equal angles, then the 2 triangles are similar. But you can repeat the same reasoning for the triangle XYZ again and the triangle XWZ. So again, they both have a right angle in W and in X. They both share the angle Z. So the remaining angle is also equal. And so again, you have 2 similar triangles. Now, from these 2 similarity between these 2 pair of triangles, you can draw some equivalent of ratios. So on the one hand, you can say that XY, so the hypotenuse of XYW, and YZ, so the hypotenuse of the main triangle, stand together as YW stand to XY. And basically, you can draw a similar equivalence between XZ and YZ, and WZ and XZ, okay? And these 2 equivalents you can re-express in the following way. You can have XY square, which is equal to YWYZ on the one hand, and on the other hand, you can have XZ square, which is equal to WZ and YZ, okay? So you take these 2 equivalents, you put them together, and by doing some very simple algebra, and by of course, take into account that YWZ is equal to YZ, you obtain the theorem that you wanted to prove. So basically that YZ square is equal to XY square and XZ square, okay? So this is the proof that, according to mathematicians, explain Pythagoras theorem. So the question is, why is this proof is explanatory? And basically, several arguments have been given in favor of this perspective. The first is that this proof doesn't rely on any particular construction around the right angle triangle. It's basically based on the similarity of triangles, which is a very general property, but generality often is associated to the explanatory power of arguments. So that's the reason why they think it's explanatory. Another argument that's been given is that the proof relies on a property that only right angle triangle possess. So only right angle triangle can be divided by the height in 2 triangles, and you can prove the similarity between them. So this is, as philosophers would say, is an essential property of right angle triangle, but precisely because the proof relies on this essential property, then the proof is explanatory. And finally, it has been said that the proof actually revealed the reason why the theorem is true, and the reason amount to the fact that if you have a similarity between triangles, then you can infer some equality of ratios. Okay, so So this was the example to better illustrate this idea of explanatory proof. And this idea of explanatory proof and their distinction from proof that is a theme that crossed the whole history of philosophy. So you can find analysis of them in Aristotle, but also in Bolzano or Frege. And nowadays it's at the center of a great debate in philosophy of mathematics, and the debate takes the name of explanation in mathematics, because these proof why are also called explanatory proof, but they can also be seen just as an explanation in mathematics, as they are a type of explanation. Now, in this debate, I would say that the central question is what makes a proof explanatory? So once we recognize that there is this distinction between proof that and proof why, we can ask the question, okay, what makes this proof why in a certain sense? In other terms, what feature endows certain proof with their explanatory power? Okay, and this is precisely the question that I aim to tackle in my talk. Okay, and I will try to provide an answer to this question, and the originality of the answer lies in the fact that I'm gonna use the resources of logic to provide a model that account for explanatory proof. And in particular, since we are talking about proof, and in logic there is proof theory that already account for proof, I'm going to use the resources of proof theory in what I think is a very natural way. So I'm going to rely on two formalisms. The first is what has been called deep inferences, and the second is this idea of transforming systematically axiom into rules. So the plan of the talk is the following. First, I'm going to show how and why we should pass from informal mathematical explanatory proof to their formal counterpart. Then I'm going to analyze the logical level of this formal counterpart. Then I'm going to move to the mathematical level. And the work that I'm going to present at the mathematical level is actually a joint work with Hélène Pimentel. And I will close the talk by coming back to the explanatory proof of Pythagoras theorem, and I'm going to show how everything I've said before naturally applied to this proof, so that you can see why, in a certain sense, it's explanatory according to the model that I want to propose. Okay, so let me start by motivating this move from informal to formal explanatory proof. So the idea is rather simple. So we want to understand what feature characterize explanatory proof. And the idea is that we can actually do that in a very rigorous way if we move from the analysis of informal proof of mathematical theory to their formal presentation in terms of proof trees. And so we can basically rigorously analyze each element of the informal proof, the assumption, the conclusion, and other elements. We give a formal counterpart in terms of assumption, conclusion, and rules. Okay. And so the idea is that once we have this formalization, those mathematical proofs that are regarded as having an explanatory power, they will all display the same structure. So it's the structure that will reveal their explanatory power, and in particular, they will all involve explanatory rules. So the explanatory rule is really the key to understand the explanatory feature that distinguish proof Y from proof that. So I'm going to explain this, clarifying this crucial point a bit better. So suppose, again, that we start from the explanatory proof of Pythagoras theorem, but we are not going to dwell on the informal presentation. Rather, we are going to formalize it as a proof tree. And suppose that the proof tree that comes out as this form, okay? And usually what we do is that we use this form to denote proof tree, or what we call in logic derivations, okay? And derivation can be seen as the logical skeleton, or just the skeleton behind mathematical proof that. And when we want to analyze derivation, basically, ultimately, what we do is we analyze the inferential rules that make up the derivation, okay? So inferential rules are the ultimate bit that we focus on to understand what's going on in the whole structure. And the idea is to do the same at the explanatory level. So the idea is that in order to understand what's going on in an explanatory proof, we need to focus on each singular step, okay? And if the step is explanatory, then we are going to denote it with this double line, okay? And the analysis ultimately will concern this explanatory step, which will be formalized by the explanatory rule. So the idea is basically to repeat what we usually do in proof theory at the inferential level, but for the explanatory level. So the explanatory rules will work at the logical level. So they might concern the connectives, but they might also concern mathematical concepts. So they might also work at the mathematical level. Okay, and of course, the feature of the explanatory rules at the logical and at the mathematical level will be the same. It's just at the logical level, they will deal with logical connectives, and at the mathematical level, will deal with mathematical concept. Okay, but the feature will remain the same. So I will first show you the logical level and then move to the mathematical level. Okay, logical level. So the idea is that, I'm going to say it again, in order to understand what's going on in the explanatory proof, we ultimately need to focus on singular explanatory step. So I went back in the literature and take into account a lot of explanatory steps that are judged so, okay, by philosopher or mathematician. And I try to isolate those features which are recurrent in each explanatory step. So I've isolated 3 features that I'm going to show to you. But first, I'm gonna illustrate some example of the explanatory step that can be found in the literature. So the first is something that you might be very familiar with. So let's assume as premises 2 is an even number and 2 is a prime number. Then you can infer 2 is a prime and even number. But it is said that this can also be seen as an explanatory step. So if you ask why 2 is a prime and even number is true, the answer is, well, because 2 is an even number, 2 is a prime number. So this simple inferential step can also be seen as an explanatory step. Okay, so let's go a bit more complicated. So again, consider the sentences at the top. You have if x is a square, then it has 4 sides. And if x is a square, then all of its sides are equal. And these are taken to explain, to be the reason why this conclusion, if x is a square, then it has 4 sides and all of its sides are equal, is true. So again, from the premises to the conclusion, not only you have an inferential step, but also this explanatory step. So a last example that doesn't concern the and anymore, but the or, just to change. So you again consider the 2, x is a natural number if it's 0, x is a natural number if it's the successor of a natural number. And again, these 2 sentences are taken to explain this conclusion, namely x is a natural number if it's 0 or is the successor of a natural number. Okay? And these are all examples basically accepted of this explanatory step. So the idea is, let's extract from these steps some features which are recurrent. And in this kind of extraction, I have partly relied on the philosophical literature and partly not. You will see in which way. So the first feature is that in explanatory step, complexity always increases. And this is a very strong philosophical idea that can be found in Aristotle as well as in Bolzano. So basically, when you explain, you are always introducing something in your argument. So in the first example, you take 2 separated sentences and you add an end. Okay, and you put them together with an end, so you move from the simpler to the more complex, and you don't lose anything in this move. The same for the second example. So here again, you introduce an end, okay, although you introduce it in a certain sense inside the sentence itself. But again, you are not losing anything. You are keeping everything and put it together. So you are increasing the complexity. And the same with the third example. Okay, you are introducing the or. So this is the first feature. The second feature, and this is also a feature which is discussed in the philosophical literature, is dependence. So basically the idea is that if you take what explained and you take what is explained, not only what is explained follows from what explained, but also you can go back. So basically from what explained, you can infer either one or the other premise. And so there is a real dependence between the two. And this, again, it is the case for any of the examples that I've taken into account. So first feature, complexity increase. Second feature, dependence. Now, the third feature is something that has not been underlined before, but I found it quite striking once we reflect again on the example that I've taken into account, and instead of focus on their content, we focus on their form. Okay, so basically, let's formalize the sentences. Here I'm dwelling with the third example. So let us move to a formalization in first order language of these sentences. I'm going to treat the x as a for all. So we have for all x, if x is 0, then is a natural number. And for all x, if x is the successor of a natural number, then is a natural number. And this formula can be taken to explain that for all x, if x is 0 or is the successor of a natural number, then is a natural number. Now, let's abstract away from the content and just focus on the form. So if we want to describe how to obtain what explained from what is explained, we need to say that there is a part of what is explained that we keep fixed, namely the part in red, and there is a part that we work on, the part in blue, and basically what we do is we break the part in blue, okay? We break the or, and by breaking the or and keeping fixed all the rest, we obtain the formulas that explain. Okay, so this is quite peculiar in logic, because in logic, typically we work with the main connective. So we would work with the for all and then with the implies and so on. But in an explanatory framework, you seem to need to be able to work inside the formulas, okay? And a similar scenario, so this idea of going deep inside the formula, I've also found it in this framework that is called deep inferences that has been introduced by Alessio Guglielmi for very different reasons, but I found very curious that it emerged again in this explanatory framework. So the idea is that, so these are the three features that characterize explanatory step: complexity increase, dependence, and the fact that you can work deep inside the formula, okay? And you want to have rules that reflect these three features. In particular, you want also to be able to work deep inside the formula, so you need to introduce some notation to do that, okay? And the notation that I'm going to introduce is this notation of context and formula in a context. And the idea is that you can consider formulas of first order logic and just having a way to rewrite them. So consider again the formula for all x. If x is 0 or the successor of a natural number, then is a natural number. And suppose you want to keep fixed the part in red, that you are going to denote the part in red with a C for context and put a bracket beside. And the bracket could be seen as a sort of zoom that allows you to zoom on part of the formula. So if you want to zoom on Zx or Snx, you're going to put Zx or Snx in the brackets, okay? And so this notation is just a way of rewriting this first order logic formula, okay? We are not changing the way we built first order logic formula, we are just changing the way of denoting them and this novel way allows us to work inside formula itself. Okay, so I have a definition for all of that, but I'm not going to dwell on it. So an important point is the following. Once you consider subformula of formulas, these subformulas might be assigned polarities that can be positive or negative. And the way of understanding polarities is a standard. Okay, so this is the definition that I've adapted from basic proof theory of Trollestra and Spitzenberg. And polarities will happen to be important. Okay, so now I really have all the means to formulate these explanatory rules. So rules where not only is the conclusion inferable from the premises, but also where you have an explanatory step. I'm gonna convey them in first order language, and I'm gonna use the sequence calculus, okay? Because I think sequence are a very powerful tool. Explanatory rules you will see are a few. I'm not gonna focus on all of them because some of them drift us away in a certain sense from the main goal of the talk. So I'm just gonna skip them in a certain sense, but those of you who are interested, they can ask in the Q&A. Okay, so the first rule I want to present is the following, is the rule for double negation. So you have a double line here, which is the sign of the explanatory power of the rule. So you can take the premise to explain the conclusion, or the premise is to be the reason why the conclusion is true. The M style N are the sequence, okay, standard sequence, and then you have formula and context. And the idea here is that you can have a formula C, which might be quite intricate, but if you have an occurrence of F in C, then you can move from F to not F. So there is something I didn't say. By the way I define context, a context could be empty, okay? So if it is empty, and even the sequence is empty, then you are back to something that we are all very familiar with in classical logic, namely this move from F to not F, okay? But the rule is that I'm proposing is much more powerful because it allows you to go from F to non-F without changing anything else, okay? So you have the standard rule when the context is empty, but you have also the possibility of not touching anything and just move from the F to the non-F. And this is to be taken as an explanatory step. Okay, then you have rules for conjunction and disjunction. I'm gonna dwell on this rule here on the left. So the rule again, you have the explanatory step, you have the sequence as before, and you have again formula and context. Okay, and here you have a circ, and the idea is that you can substitute the circ with either a conjunction or a disjunction, but to do that and apply the rule, certain restrictions need to be respected. Okay, so I won't list them all because the list would be kind of boring. You can find all the restrictions in this paper of mine. I just give you a flavor of it. So suppose here you have a conjunction. It has this formula F and G has a positive polarity in C, and it is in the scope of universal quantifier. So if this is the case, then you can break the end and get your explanans, so the F and the G. Okay, and this you can do without touching anything of the rest. Of course, the context could be empty, also the sequence could be empty, so you are back to something very simple, very familiar. But the rules, and this is its peculiarity, also allows you to work inside the formula without touching anything else. So these are two instances of this rule. The first, you can see it as formalizing our 2 is a prime and 2 is an even number, explain why 2 is a prime and even number. But you want to be able to do more. For example, you want to be able to explain why for all x, if x is a square, then it has 4 sides and its sides are equal, okay? And in this case, you have an end with a positive polarity inside a universal quantifier. So you can apply the rule and you can break the end here and get your premises, which correspond to the example that I've shown you before. Okay, you break the end without changing anything, and these two formula can be taken as explaining the conclusion. Okay, you also can have an or here. Of course, other restrictions are to be observed, and also the or can be seen as being explained by its two disjunct. Okay, if the two disjunct are true, And again, this rule holds if the context is empty, also the sequence could be empty. So we are back to something familiar, but you also have the possibility to work deep inside formulas. So again, these are two instances of, again, still the same rule. So here, just an example that goes beyond mathematics. So suppose Mary is tall or Mary is smart, and it is the case that Mary is both tall and smart. So both disjunct are going to explain the disjunction. And this is a very simple case. But suppose we land on a formula which is a bit more complicated, like for all x, if x is 0 or the successor of a natural number, then is a natural number. Here we have an OR with a negative polarity inside a universal quantifier. We can break it, and these give us the explanants that we have seen before without touching anything. So we have an explanatory step. Okay, so I cannot stress enough how restrictions are important. So I've introduced them to control the framework, because otherwise it explodes, but they have a conceptual counterpart. Okay, so let me show you this. So suppose you have this formula, which formalizes for all x. If x is a natural number, then it's either odd or even. Okay, and someone here could be tempted to say, I'm understanding what's going on. I'm going to break the OR and break the formula into two and get the explanants. That would be, in this case, for all x, if x is a natural number, then is odd. And for all x, if x is a natural number, then is even. But this would be a bad explanation, okay? If only because the explanants would be false. And luckily, there is no rule that allows you to do that, because in this case, the disjunction has a positive polarity inside of universal quantifier, so you cannot apply it. Okay, so on the other hand, this other rule is a rule that allows you to deal with cases where only one disjunct explains the disjunction. But as I said before, this rule, clarifying it in the detail would drift us a bit apart from the main goal of the talk. So I won't dwell on it, but all of you who are interested, you can ask in the Q&A. Okay, so I also have rule for negation of conjunction and disjunction. So again, it's still the same structure. You have the explanatory step, you have formula in context, you have the circ that you can substitute with an and and an or, but again, you have restriction, okay? And when you have the negation of a conjunction or a disjunction, what explain is not the negated conjunction or disjunct, but what I call the converse, okay? And the converse is just a more fine-grained way of taking into account negation. And I need that because it has been shown that if negation are not properly taken into account, they can lead to some inconsistency in an explanatory framework. But I've shown that if you use converse, you don't have this problem, okay? So you need to be careful on how you place negation in an explanatory framework. Okay, so these are the explanatory rules at the logical level. So they only deal with connectives, okay? They can work deep inside the formulas. They just increase the complexity. And in each case, you have the dependence between the two. And actually, between premises and conclusion, actually, this is a theorem that you can prove about them. So you can prove that explanatory rules that I've just shown you are all and only those rules that respect the three conditions that I've shown you that characterize explanatory step. Okay, so of course, each of the conditions has a formal counterpart, so that's how you can prove the theorem. Another theorem that you can prove, and to me this is very important, is that if you take the classical sequence calculus for first order logic, you can show that these explanatory rules that I've shown you are all admissible in it. And this is important because basically admissibility says that if I take the classical sequence calculus for first order logic and add the explanatory rules, I'm not changing the explanatory power of the calculus, okay? So the set of theorem I can prove remains untouched. But this is exactly what's going on between proof that and proof y. So think of Pythagoras theorem. You have 9 proofs of the Pythagoras theorem. Your explanatory proof doesn't allow you to prove more about right angle triangle. It allows you to prove the same, just in another way, in an explanatory way. okay? And so basically these lemma, in my opinion, show you that at the formal level, the explanatory rule preserves this feature. Okay, so this is what I wanted to say about explanatory rules at the logical level, but now I need to move also to the mathematical level. Why? Because my ultimate goal is to have a full analysis of the explanatory mathematical proof of, for example, Pythagoras theorem. And I know how to deal if there are some logical explanatory step in it, but I don't know what to do with all the rest of the proof. Okay, so I need the mathematical level to be there as well. And as I said, this is part of the joint work with Hélène Pimentel. So our starting point to deal with the mathematical level are what we have called conditional axioms, okay? And conditional axioms are formulas of the following form. So you have a predicate here, G, and a formula F, and you have an equivalence between the two, and basically you can take F as defining the predicate G. And it defines the predicate G under a certain condition or hypothesis, whatever you want to call it, which is another formula. Of course, the hypothesis, so this H could be a truth, and so you can just take it away, and you just have an equivalence between a formula and a predicate, okay? So this is what we call a conditional axiom. So why are conditional axioms the starting point to go at the mathematical level? So first, let me observe that conditional axioms are a generalization of the concept of definition clauses, and definition clauses have already been analyzed in proof theory by Schroeder-Heister, and Miller and Thiel. Also, conditional axioms are similar to the so-called guarded horn clauses that have been analyzed in this famous paper of Ueda, okay? In an explanatory framework, conditional axioms are central, okay? And why are they so? Because as it has been observed in the philosophical literature, each time you have an explanation, you have generalization that make the explanation work. But conditional axioms are the formal counterpart of generalization. So if you want to get what's going on in an explanatory proof in a formal way, you need a formal counterpart of this generalization. And that's what conditional axioms do, okay? So for us, they are crucial. And the idea is the following. We are going to use the conditional axiom to obtain the explanatory rules at the mathematical level, okay? So these are the ingredients to get, again, this explanatory step, but at the mathematical level. So how do we do that? So first, you can put together more than one conditional axiom, so you can have a set of them, as long as two restrictions are observed. The first is that if you have a conditional axiom that define a predicate G, you cannot have another conditional axiom that define G in another way. Okay, this is the first restriction. So basically, we have framework where definitions are unique. And the second restriction is that if you have a conditional axiom that define the predicate G, then you cannot use G to define another predicate, okay? So you can put conditional axiom together, but they need to observe these two restrictions. Okay, then you take the conditional axiom and you systematically can transform them in the following rules, okay? And the rules you see allows us to move from F to G, and F to G on the left and on the right side of the sequence, and we can move under certain hypotheses, okay? Of course, the hypothesis could be empty, and the rules are even simpler. We just move from F to G and from F to G on the right and on the left of the sequence. Okay, so what do we do with these rules? Basically, we take the classical sequence calculus for first order logic, and we can add as many rules, as many pairs of rules as we need to match first order logic plus the conditional axiom that we want, okay? And we can prove that the calculus so obtained is sound and complete with the first order logic augmented with the conditional axiom that we need. Not only that, so this is basic, but also that the sequence calculus so obtained keep on satisfying the nice feature of the classical sequence calculus for first order logic. So weakening is still admissible, logical rules are still invertible, and the cut rule is still admissible. To prove that the cut rule is admissible, we need to use a sort of stratification. Okay, we can discuss it in the Q&A. Okay, this is all nice because you have the explanatory proof, you are going to have the generalization in it, but you transform the generalization, you formalize it in a conditional axiom, then you get your rules, and you know that you can have a sort of mathematical theory in the form of a calculus. But this is not enough, because what we want are explanatory rules, okay? Namely, rules that can work even for mathematics inside context, okay? But we can show that we can have also that we can also move from a F to G inside formulas, okay? So suppose you have a C, and this is the rule on the right. You have a formula C, and in C you have an occurrence of H implies F. Then you can move to H implies G. So basically you can substitute the F with the G under certain condition, and you can do that when the F is in the consequent or in the antecedent, okay? So it's basically the same as the rules that I've presented before, but that can work inside context, okay? And these are admissible. Of course, if the context is empty, we are back to the rules that we used to have before. And also, if the H is empty, then we can just move from the F to G inside context, where the polarity of F can either be positive or negative. So you basically have the F, and you can just substitute it to G. Okay, so now we really have all the elements to analyze the explanatory power of this proof Y. So how do we do that? We start by considering an explanatory proof. We extract the conditional axiom it contains. Then we transform the axiom into rules, and we add them to the classical sequence calculus for first order logic. We know that the calculus so obtained keep on enjoying the nice property of the sequence calculus for the first order logic. And plus, we know that in this calculus, both the logical and mathematical explanatory rule are admissible. So we are going to use this rule to formalize the informal mathematical proof we started with, okay? And we are going to know that the application of each of these explanatory rules will be the sign of the explanatory power of the proof. So we can map exactly where the proof is explanatory. Okay, so I'm going to show you how to do that. So how to apply this methodology with the explanatory proof of Pythagoras theorem that I've started with. Okay, so we go back to the explanatory proof of Pythagoras theorem. I hope you remember at least a bit of the details. So the idea is that the first step, as I just said, we need to isolate the conditional axiom on which the proof relies. And it turns out that this proof relies on two conditional axioms. So the first is the following. So basically is the axioms that say, so TR, formalized triangle, and obtain when you can draw the 8 and obtain two triangles from a given triangle. And sim is the similarity between two triangles, okay? So I'm going to read what is written below. So if XYZ is a triangle, and XYW is a triangle, and XZW is a triangle, and XYW and XZW have both been obtained by drawing the 8, XW, and you have the similarity between XYW and XZW, and the main triangle, sorry, then, so if all these condition is respected, this is going to be our H, then you have an equivalence between, this is the predicate that we are going to define, and a conjunction, okay? So the predicate basically say that the square of YZ is equal to the sum of the square of the two sides, and on the other side you have a conjunction between XY square, remember it was the way we rewrote the equality of ratios, and YW, YZ, and the same for XZ square, okay? So basically this conditional axiom is saying that under a certain hypothesis, you have an equivalence between these equivalence and this formula. Okay, so this is our G and this is our F. And this is our hypothesis H. And the idea is that we can systematically transform it in the following two rules, where we move from the end to the equality on the left, on the right and on the left of the sequence under a certain hypothesis H. Okay, and this is the first thing we need. And then we can isolate a second conditional axiom, and the second conditional axiom is going to say that, again, under a certain hypothesis H prime, let's say, again, that this is a triangle, this is a triangle, XWZ is a triangle, and XYW and XWZ have been obtained from XYZ by drawing the height. Then we have that the predicate right angle, if and only if you have the similarity between XYW and XYZ and XWZ and XYZ. So this is the second conditional axiom we use. So under certain condition, a triangle is rectangle if and only if there is a similarity between the triangle you can decompose it with. So this is what this is an essential property of right angle triangle. Only right angle triangle, as I said at the beginning of the talk, can be decomposed into similar triangles. So this is the second conditional axiom, which we can transform into the following rules, where we can move from the similarity to the right angle on the right and on the left of the sequence under a certain hypothesis H prime. Okay? So we have our explanatory proof. The proof relies on two conditional axioms. Each conditional axiom can be transformed into a pair of rules. We can add this rule to the classical sequence calculus for first order logic, and we know that this new calculus is going to enjoy soundness and completeness, cut eliminability, weakened admissibility, and so on. And we also know that we can formulate rules which are very similar from the one before, but that can operate inside the context. So we can move, so these are exactly the same rules that I've just shown you, but which can operate inside the context, okay? So you can move from the conjunction of these two equality to this one, okay, on the inside the formulas. And also you can move from the similarity to the right angle inside the formula, so without touching anything else. And these you can take as explanatory step in the mathematical theorem, okay? Why explanatory step? Because again, so you can see as introducing the concept of right angle, so you are introducing something new, the complexity increase, and then you have the dependence between the two, and then you are working deep inside formula. So again, you still have all the features that you used to have at the logical level. So now we really have all the elements to formalize the explanatory proof of Pythagoras theorems. So the proof started by, again, observing that this is a triangle. I'm not going to repeat it all. There are three triangles and they are similar among each other, and if this is the case, then you have that xy square is equal to yw yz. So I'm going to write this in a shortened way, and you can repeat it for xz square. Okay, these were our initial observation. So these are going to be the leaves of our proof tree. So now we have this formula, and we can focus on just the bit in red of these formulas, which is the consequent, and we can actually use an explanatory logical rules to put the two formulas together and introducing a conjunction without changing all the rest. So this is an application of the logical rules that I have explained in detail about conjunction and disjunction. It is applicable in this case, and this can be seen as an explanatory step. So if you want to know the reason why this formula is true, the one which are at the top are going to be the reason why it is true. And you can still work on this part of the formula and introduce and reduce, in a certain sense, the conjunction in this way. Okay, so here you are applying the rule that allows you to move from the conjunction to this equality inside the formula without touching all the rest. Okay, and now you move the analysis to the similarity of the triangles, and here you can introduce the fact that it's right angle. And each step is an explanatory step. Okay, and from this formula you can eliminate the y and infer Pythagoras theorem. So this is a formalization of the explanatory proof, the informal mathematical explanatory proof of Pythagoras theorem that is faithful to the original one, but where you can see in each step what is going on. Basically, each step is explanatory. Okay, this is not often always so. So you might have mathematical explanatory proof where you have some steps which are explanatory and some steps which are just inferential. But the important thing is that you can isolate the explanatory step. Okay, so you can recognize exactly when the proof is explanatory. Okay, so the idea is that by means of this analysis, we can confirm this intuition that mathematicians have that the proof is explanatory, but we can also single out each explanatory step. And in Pythagoras theorem, all the proof is explanatory. So it's a particular nice case. Okay, so let me draw some conclusion. So basically the aim of, so the main task of the talk was this idea of tackling explanatory proof and try to see in a systematic way what feature of the proof endow the proof itself with an explanatory power. And we have tried to provide an answer with using logical tools coming from proof theory. I found this way of dealing a very natural way because we move from explanatory mathematical proof to proof theory, which is the logical tool made for dealing with proof. So in our analysis, a central place has been occupied by these explanatory rules, okay? So the key to understand what's going on in explanatory proof are these explanatory rules. But explanatory rules have already been shown to be useful in other contexts, okay? So not only, I think they have a meaning in this philosophy of maths literature, but they can also be used elsewhere. So a first application, I've done it with my co-author Brian Hill in the field of explainable AI, where we have shown that there is a link between explanatory rules and what Darwish and his collaborator call sufficient reason. So basically, you can use, in a certain sense, explanatory rule in this area of expanding area. A second application still in the same direction with other two co-authors, Denis Bonnet and Adrien Champigny, where we have used, again, this mathematical explanatory rule to analyze the mathematical capacity of large language models. So again, it goes in the direction of large language models. So these are two applications that have already or are in course of being developed, but I think there are many others. So here is a quick list. So what I've tried to single out are explanatory rules for first order logic, but you can wonder about explanatory rules for modal logic or substructural logic. And when you isolate them, you can also use them, for example, again, in explainable AI, they could be useful, I think. Second path of research, so there is this trend which is called proof theoretic semantics, where basically the idea is that rules provide the meaning of the constant they introduce, but the rules that have been analyzed so far are inferential rules. Now, once explanatory rules are on the market, you can ask the same question. You can ask, well, do explanatory rules provide the meaning of the constant they deal with? And if so, in which way they differ from inferential rules? So you can re-ask the same question that have been asked for inferential rule for explanatory rules. Also, everything I've been developed is syntactic, but it would be nice to have a semantic counterpart. And finally, there are many explanatory proofs out there, And I think that if you apply the method that I've shown, you can maybe find new features or analyze them in a more fine grade than what has been done so far. And that's it. And thank you for your attention.
Yes, thank you so much for the talk, Francesca. Very nice, very clear and well presented. If you have a question, you can ask it in the Q&A, and then I will
There
go
are
over
already
it.
some questions.
Yes, I already saw some.
Yeah, just read them. I also have some questions, but I'm not going to write them, but I'll make them later.
Okay, great. I'll first read a few and then I'll go to you, Agatha. So the first one is from Giacomo Lenzi, who asks, are Aristotelian syllogisms, he says, so are Aristotelian syllogisms never explanatory?
I don't know if never, but the one I know, it's hard to consider them as explanatory. Because it's like you always do so an explanatory proof is really an analytic proof where you don't lose anything, you just increase while this complexity, okay? While in syllogism, typically you basically cut something from the two premises to reach the conclusion. So there is something missing, and this is why I would say that they are not explanatory.
Okay. Then the next question from Schroeder, Heister, Peter. Well, first he says, excellent and very well presented, as expected. And then just a remark on the stratification conditions. I would recommend to discuss them. Calling them into questions would lead to the non-well-founded case, which opens up a vast new field of application.
Okay. So the stratification, I don't know if I understood correctly the question. So the idea is that when you want to prove the cut eliminability, when you add this conditional axiom, the standard to the height and the complexity, so the standard measure where you do the inductive hypothesis are not enough because you are dealing also with predicate. So you need to stratify the predicate. And once you stratify the predicate, you can apply your induction on this stratification.
Okay, thank you. Then we go to the question from Mirko Tagliaferri. When you talk about complexity increase connected to an explanation, is this measured only in terms of number of connectives? How does this relate to explanations in other fields?
Okay. So the complexity increase is like the point of explanation. So more generally speaking, so the difficulty bit when we analyze explanation is the fact that explanations are always asymmetric, okay? So there is always a directionality and you need to account for this directionality. And this is where all the previous philosophical account have failed, because each time they've proposed a criterion for this directionality, they've always found counterexample. So the idea is that if we go back to Aristotle or Bolzano, they isolate as the criterion for symmetry or directionality complexity. And in logical terms, it's easier to understand this complexity in terms of this introduction of a new connective. But once we go at the mathematical level, it becomes more tricky, okay? And with the conditional axiom, it's kind of easier again because we take a predicate to be defined by a formula, and we consider the predicate as always increasing the complexity because it's the new element that we introduce. And so we have this increase of complexity in this way. Okay? I don't know, again, if I was clear or...
Okay, then we have another question on complexity from
wait. There is Schroeder, Heiser, Peter. He answer your comment saying yes, but do we need cut at any price?
Do we need cut at no, not at any price, in the sense that as long as the explanatory proof, the formalization of the explanatory proof doesn't use the cut, then the cut could be there in the theory, okay? But of course, if we know that the theory we are dealing with is cut-free, then in a certain sense, we can be more hopeful of finding the counterpart, the formal counterpart of the explanatory proof, if we know that the theory we are working with is cut-free. So it's not at any price, but it's very nice to have it. Let's put it this way.
Okay, then now we can go to the question from Laura. You mentioned an increase of complexity for explanatory steps. How do you measure complexity in that case? As in, is there a mathematical definition for the complexity?
So I have, so on the logical bit, in the paper that I've quoted before, I have a rigorous definition of the increase of logical complexity. Okay, so I have defined stuff to see that you, in each explanatory step, you have an increase of logical complexity. For the mathematical bit, I cannot be as rigorous because you are dealing with mathematical concept, but I have a paper in Philosophia Mathematica where I try to establish a measure to compare different mathematical concepts complexity-wise. So I have a measure for both the logical and the mathematical side. The logical side, it's very precise, is like a measure, well-defined and so on. For the mathematical bit, it's more a method to compare mathematical concept, but I'm afraid I cannot be as rigorous.
Okay, then we have the next question from Pavio. Have you explored the application of your proposal to the proof analysis program of Negri and von Plato? And more general, what other case studies do you have in mind?
So what does it mean for the program of Negri and von Plato?
Whether you have explored the application of your proposal to this proof analysis program?
Yeah, but I don't know the proof analysis.
Okay.
Okay, but you can answer the second part.
Yeah.
What other case studies do you have in mind?
So there, there are. So there is a book of Mark Lange, which is called Because Without Cause, and there are really many cases of explanatory proof. So what I've done is to take into account all these cases and see whether the methodology that I've presented today work, and it actually work in each of these cases. Then, of course, the literature is a literature in theory. So there are new explanatory proofs that are studied, analyzed, proposed, and in each time you should test this methodology again. But it has already been tested on a fair amount of cases.
Okay, and Pavio just added an explanation that says to use your proposal to explore the properties of mathematical theories in the style of Negri and von Plato.
Ah, okay. Yeah, it could be also used to study mathematical theory from an explanatory point of view.
Great. Okay. Then there's another question from Mirko, who asks, are formulas in the context always assumed to be different from the formulas in the explananda, or could the same formulas appear both in the context and in the explananda?
So is he asking whether the explanans and the explanandos could be the same? I didn't get the question, sorry.
Whether, I'm not sure, Mirko, maybe you can elaborate, but whether the formulas that you can put in the context, are they always assumed to be different than the ones in the explananda?
Yeah, sure. So if you have a context, so when you have a context and an explanandum you are considering, then the explanans, yes, should be different because nothing can explain itself. So the relation is assumed to be irreflexive. But this is not just me, it's what is generally assumed in the literature on explanation.
Okay, Mirko elaborates and says that context hides some of the formulas. Could those be the same as the ones left under analysis?
Sorry, say it again.
So the context,
Yeah.
they hide some of the formulas. So you kind of, right, because they're part of the context.
Yeah, exactly.
And then could those be the same as the ones left under analysis?
So you
Mir-
the
yeah.
context. So you have an application of the rule where the context, of course, in the application of the rule should be kept fixed, right? But then when you move to another step, as in the proof of Pythagoras theorem, you can move to another part of the formula where you want to work on. And in this case, the context will change because you are moving on another part. So you can move context from one rule to another, but not in the same rule.
Okay. Mirko, I hope if that doesn't answer your question, Mirko, otherwise I can also allow you to talk and then you can ask it later, but let me know if that's necessary. Yeah. Then the next question is from Blaž, who asks, have you tried analyzing more complex mathematical proofs from this explanatory perspective? And does anything change, or is it enough to discuss the kind of examples that you've presented?
No. So you need to apply the methodology as much as you can to see whether it kind of can take into account all of the cases. Of course, the more complex you go, the more intricate explanatory proof you explore, the more intricate the more difficult is to apply the methodology. And so the difficult bit is to extract from the explanatory proof the conditional axioms it uses. This is the difficult bit. Once you have the conditional axioms, everything goes smoothly because you have all the means to transform the axiom into rules and so on. But the difficult bit is to recognize what in the proof constitute the conditional axiom.
Thank you. And then from Valeria, you mentioned generalization to modal and substructural logics, but not to intuitionistic logic. Is there any reason for that?
No, intuitionistic logic is I'm really sorry to have missed intuitionistic logic. This is a very good question. Yes, intuitionistic logic is definitely a field where you should explore explanatory rules, especially because explanatory rules have this constructive flavor, okay, where you exactly because you increase the complexity in each time, I think they have something constructive in it. So I think that the field of intuitionistic logic would be a very nice field to explore explanatory rules.
Let me add one question to what Valeria said. So, like what you have these three, say, postulates like dependencies, but like this double negation rule, it's kind of strange in with regard to the dependencies. So it's like it seems that you are explaining if you have not A, then the explanation is A, but that's not the case clearly in intuitionistic logic, for instance.
So so you wouldn't have that in intuitionistic logic. Clearly, because so the explanation only goes from F to not F.
But then how about the dependency?
The dependency is just that typically when you explain a formula with another formula or a pair of formulas, you have it's like all the rules are like invertible.
Yes.
Yes, but the explanation only goes one way. And that's what is peculiar of explanation. You have a dependence on the back, but the explanation goes just one way. So it's like in the mathematical case, you have an equivalence between a predicate and a formula, but the explanation only goes one way. It's,
okay.
yeah. So this is what makes any explanatory step so powerful, because you feel like this equivalence, but you need to choose in a certain sense which way you want your explanation to go, and you always choose when the complexity increases.
Okay. Then we have the next question from Xavier, who asks, does your approach to explanation allow for the possibility of competing explanations? In common sense reading, this makes sense.
So if by competing explanation, you mean that, so suppose you have a theorem and you have two proofs, and actually both are considered explanatory. And then you formalize them with my methodology, and you can see exactly where the proof goes explanatory, okay, with the explanatory step. And suppose that, so this is very naive, but suppose you count the number of explanatory steps in each proof, and you want to compare them on the number of steps, then if you want to compare competitive explanation in this way, you could, I guess. I don't know if it has any interest for the literature, but you can distinguish the degree of explanation.
Okay. And then there's a comment I get from Valeria that says that this line of work should be very interesting for people working on formalized mathematics using proof systems, where maths is very different from the meaning of formal you're using. Then for next question, an anonymous entity asks, could explanatory proofs help in justifying or interpreting new axioms or operators in a modal logic system?
No, I wouldn't see how. No. So the idea is that you really need to think that in explanation, so you first lie down a theory, and then it's kind of you extract out of the theory this explanatory power. So it's not the other way around. It's not that first comes the explanatory power and then you go back to the theory. The theory in a certain sense is already, it's assumed to be there.
Okay, and then a question from Fabio again. Why is there no explanatory rule for the conditional? Would this mean that the conditional is essentially a mathematical operation?
Yeah, this is a very good question. So yeah, you could formulate a rule for the conditional. You could, because the conditional you can, you are in classical logic, connective are interdefinable, so you could, but in all cases of explanation that I've seen, the conditional remain fixed. And you just operate on what is on the side of the condition. So by now, I'm firmly convinced that you don't reduce the conditional. The conditional is, it's like a mathematical operator. It's there, and you are going to move on the sides. This is my feeling. So you could have rules for the conditional, but they would be kind of useless rule in the sense that I never saw an application of them.
Okay, so there was a very lively debate. So there are no more questions, right? No. Yes. So, Francesca, thanks really a lot for your very inspiring talk. And let me also thank Andrea Hackel for all her support for actually not only for this talk, but for the whole series of talks for women in logic. And hope to see all of you in March. And details will be ready soon, let's say.
Thank you again for the invitation, for all the questions also.
Bye.
Bye.
Can we close it? I assume yes, right?
Yeah, I think so, yes.
So, okay, I already ended this live stream.